Hello, ladies and gentlemen. This is Ms. Koken. We are back in Chapter 2, Modeling Distributions of Data, this time in Section 2, Density Curves and Normal Distributions. Our objectives for this section include estimate the relative locations of the median and mean on a density curve, use the 68, 95, 99.7 rule to estimate areas in a normal distribution, use Table A or technology to find the proportion of z-values in a specified interval, the z-score from a percentile in the standard normal distribution. Use Table A or technology to find the proportion of values in a specified interval or the value that corresponds to a given percentile in any normal distribution. And last of all, determine whether a distribution of data is approximately normal from graphical and numerical evidence. Our vocabulary includes density curve, equal areas, balance point, normal distribution, normal curve, bell-shaped, 68, 95, 99.7 rule, proportion, probability, standard normals distribution, Table A, assessing normality, and normal probability plot. There are a few strategies that we're going to employ in every chapter, and the first one is to always plot the data. Once we've graphed the data, of course, we're looking to see if there are any patterns and if there are any departures from patterns. We also need to calculate numerical summaries to help us have an understanding of the center and spread of the data. We're going to add one more step to this strategy, and that is to sometimes use a smooth density curve to describe our data. And we've got an example here. We can see that this histogram was covered by a smooth density curve in red. This histogram shows the scores of all 947 7th grade students in Gary, Indiana, who took the vocabulary part of the Iowa Test of Basic Skills. Let's describe the histogram. The shape is unimodal and approximately symmetric. A center peak between 6.5 and 7. A range from 2 to 11.5. No gaps and no apparent outliers. Density curves come in lots of shapes and sizes, but basically what we're going to be doing is treating this as a probability distribution. And when we look at specific area under the curve, we're going to look at that area as a proportion of the total area of one that is under the curve and above the axis. So this was a density curve. Once again, density curves can come in all shapes and sizes, but they do all follow some specific rules. And they are: a density curve is always above the horizontal axis, meaning there are never any negative values, negative area. And the area underneath the density curve is equaling 1 always. And a great way to remember this is sometimes we are using these density curves as probability distribution curves, and probability always totals to 1. So we're going to use some terms almost interchangeably. Proportion of observations is going to mean the same thing as area under the curve, and that's going to end up meaning the same thing as probability. We need to remember that the curve represents the overall pattern of the distribution, but not the outliers. And last of all, we need to remember that no density curve exactly describes a real set of data. One of the things that we talked about before was that in a symmetric distribution, the median and the mean are very close to one another. In this perfect curve, they're exactly the same. And in a skewed distribution, the mean is going to be slightly or a lot closer to the tail than the median. The median is always going to be what we call that equal areas point. And that is just what it sounds like, the same amount of area above and below the median. The mean is what we call the balance point in the distribution. And if you can imagine that your density curve is solid and you're trying to put a pencil underneath it so that it will be perfectly balanced, where you see that happening, that's where you can think of the mean being. This brings us to a check your understanding. So pause the video to work on this, and when you're ready to advance to the next page of notes, turn the video back on. One very important type of density curve is known as the normal distribution, and we'll be working with that one a lot this year. They share some specific characteristics that we're going to list now. All normal distribution curves are bell-shaped, are symmetric, and are single-peaked. And when I say bell-shaped, you see this outward flare up? That is what it means by bell-shaped. So don't draw it like a half circle when you draw the normal distribution curve. Normal distribution curves can all be defined by their mean and their standard deviation. And the notation that we use is n, and in parentheses, mu for mean and sigma for standard deviation, but obviously we would put the actual values for the mean and standard deviation in the parentheses. Because of the symmetry, the mean and the median are at the same location, at the center peak. The standard deviation can also be located by sight on the normal distribution curve. And basically what you're looking for is where the curve changes its curvature. So where it goes from upward facing to downward facing. And that's on either side. So this is what we're looking for. And basically it's going to be locatable right at that location. You can see I found it on the left hand side. We've already seen it on the right hand side. Where the graph changes curvature is called the point of inflection. Normal distributions are important. However, we need to remember that they're not the only probability distributions that we're going to be working with this year. So be wary when you read a problem, when you read a story behind a problem, make sure that you first are looking for what type of probability distribution it follows, and then you can proceed with problem-solving strategies. Let's talk about the 65, 99, 95, 99.7 rule. This is also called the empirical rule. And what we're looking at here is the density curve that's associated with the Iowa vocabulary test for the school children that we saw a few minutes ago. We can see that this curve is symmetric, single-peaked, and bell-shaped, and the normal curve can be defined by its mean and standard deviation. We have some specific numbers marked on the axis, and I just want to go through what those are. If we start out with the mean and subtract the amount of the standard deviation, we get to 5.29, and that is the first number we see on the left of the mean on the graph. If we add one standard deviation, 1.55, to the mean, 6.84, we get 8.39, which is the first number to the right of the mean on the graph. Let's try adding an additional standard deviation on the right-hand side and subtracting an additional standard deviation on the left-hand side. When we subtract or add two standard deviations to the mean, we come up with the next set of numbers, 3.74 and 9.94. Let's add and subtract one more standard deviation on either side. When we subtract and add that additional standard deviation, we see that we end up with these last numbers, 2.19, and on the right-hand side, 11.49. What do these numbers mean? Well, this is another thing that the normal probability distribution does. It follows this 68, 95, 99.7 rule, which is also called the empirical rule. And the empirical rule tells us how much of the data we can expect to see how far away from the mean. So within one standard deviation of the mean, or between 5.29 and 8.39, we expect to see 68% of the points of our data. Within two standard deviations on either side of the mean, we can expect to see a grand total of 95% of the observations. And within 3 standard deviations, we expect to see 99.7% of the data points. Are there any data points outside 3 standard deviations in a large set of data? Yes, absolutely, there can be. And you can see that through, there is a little bit of area under the curve on each of the tails. It's just very unusual to have any of those values. So this is what the empirical rule is all about. Sometimes we'll be able to solve problems without using the calculator and without using the data tables, because we'll actually be able to just use the 68, 95, 99.7 rule and determine what the values are or how much area is under the curve. The empirical rule is only for normal distributions. And we will use the empirical rule to test data and see if it does fall within those ranges, then we will be able to assess that it is normal. Let's take a look at an example. If the distribution of ITBS vocabulary scores for 7th graders in Gary, Indiana is normal with a mean of 6.84 and a standard deviation of 1.55, then what percent of the ITBS vocabulary scores are less than 3.74? Show all work. Showing work is going to start with a graph. Pause the video now and draw your normal distribution curve and label it. We calculate that when we subtract 2 standard deviations from the mean, we end up with the 3.74. What we want, we're interested in the area to the left of the 3.74. We know that that minus 2 standard deviations is associated with the 95%. And so what that means is the area between is the 95%. So on the outside is the remaining 5%. So 5% is this piece and this piece. So half of it is 2.5%. So the answer to the question is the area to the left of 3.74 is 1/2 of the 5%, or 2.5% of the area under the curve, and that represents the percent of the vocabulary scores that are less than 3.74. Let's move on to question B. It says what percent of the scores are between 5.29 and 9.94. We need another picture. So let's draw another normal distribution curve. I will make mine a little bit more symmetric than my curve on A. Okay, curve is drawn. Now let's label it with the mean and 1, 2, and 3 standard deviations away from the mean on the left and on the right. Now let's shade the area of interest between 5.29 and 9.94. Now let's figure out how much of the area under the curve is shaded in, or what percent of the scores are between 5.29 and 9.94. We know it's going to be 68% plus, and then it's going to be 1/2 of the difference between 95 and 68%, or 68% plus 13.5%. 81.5% of the scores fall between 5.29 and 9.94. And again, this is not the only way to solve this problem. We know in math there are often many different ways to get to the same answer, to get to the correct answer. But this is one way that we can do it using the empirical rule without using any of the calculator features or functions associated with the normal distribution table. This brings us to another check your understanding. So I'm going to ask you to pause the video, work on this, and when you're done and ready to proceed with the notes, you can turn the video back on. Imagine that what we try to do is find the z-score of every observation in the set of data, and graph the z-score on our normal plot. Based on our understanding of linear transformations that we talked about previously, we know that the shape of the new distribution will be normal, the mean will be 0, and the standard deviation will be 1. Even with the standard normal curve, which is when all of the observations have been standardized into z-scores, we know that the 68, 95, 99.7 rule still applies. But what happens if we wanted to find something in between that wasn't exactly following the empirical rule? Well, then we would need some other tools. And what we use is the standard normal table, Table A in our textbook, also in the formula sheet on the AP Statistics exam. This is a little excerpt from it. Let's take a look at some of the features. To begin with, the shaded area on the curve up above the table is on the left. So that's indicating to us that this table always reads from left to right. Next, I'm going to draw your attention to the Z column and the Z row. This is how we find the specific z-score that we are looking for. If we were looking for the z-score of negative 2.64, we would go to the negative 2.6 row until it intersected with the 0.4 column. The value that lies at the intersection of the column and row in which we have an interest is going to be the proportion of values that lies to the left of negative 2.64. Sometimes we want a right-handed proportion, and in that case what we would do is subtract from 1. So this is only a small excerpt of our Table A, standard normal table. We have 2 pages to it. There's a left-hand side and a right-hand side. The left-hand side is the negative side, or from the negative infinity to the mean of z equals 0, and the other side is from 0 to positive infinity. If we want to find the proportion of observations from the standard normal distribution that are less than negative 1.78, let's find that location on our Table A. We found the z-score and we found the proportion, so the next thing that we're going to do is follow the instructions and sketch a normal distribution curve and shade the area of interest. We're going to be doing a lot of sketching and shading because it really does give us an idea of what's going on in the problem and helps us to avoid errors. The next thing that we want to do is find the proportion of observations from the standard normal distribution that are greater than negative 1.78, and you guessed it, we're going to be doing some subtracting now, but we're going to sketch and shade again. We subtract the proportion that we found for the less than in order to find the area that is greater than, and you can see that we've shaded on the right hand side instead of on the left hand side. So we end up with a proportion of 0.9625. Here we can see the 2 full pages of Table A. They both read from the left, but you can see that one is the negative side from a z-score of negative 3.49 all the way to 0. And here we have the positive side, which is from 0.5 all the way to 0.9998. All right, we've got another exercise to try out. This time we want to find the proportion of observations from the standard normal distributions between negative 1.25 and 0.81. First things first, sketch and shade. Pause the video and turn it back on when you have sketched the area of interest. Here's our area of interest. Now let's find the corresponding areas on the table. Remember that the table always reads from the left, so we're going to have to be doing some subtracting in order to get the area that we want. We're going to start on the positive side with the 0.81. So there's the 0.8, here's the 0.1, and we end up with 0.7910. Remember that the 0.7910 reads from the left all the way up to the z-score of 0.81. Next, we're going to look for on the negative side, the negative 1.25. And we find that value is 0.1056. That one also reads from the left, so we've sketched that. And basically what we want to do is subtract the green one from the purple one. And we find that the area of interest, or the proportion of observations in the area of interest between the two z-scores of interest, is 0.6854. We could also call that, if we wanted to, 68.54%. This is all great, but we know that problems in the real world don't always come from one direction, so we want to know how to be able to work backwards so that we can start with the area and find the z-score. If we want to find the z-score associated with the 90th percentile of the standard normal curve, the very first thing that we're going to do is look for the 0.9000 entry. And we find when we look at the table that there isn't one exactly like what we need, but there is a close one. And this is the closest one, 0.8997. So we started with the percentile in the middle, and now we're going to look for the z-score that goes with that number. And we find that the z-score is going to equal 1.28. Okay, that brings us to another check your understanding. Try these problems out and turn the video back on when you're ready to proceed with the notes. You'll want to know how to use the calculator instead of table A, because sometimes that can be a real time saver. If you're trying to find the proportion or the percentile using the z-score, you're going to be using the feature normal CDF. And you get there by hitting the second key and then the vars key. That takes you to different probability distributions. Number 2 is the normal cumulative distribution function, and that's the one that we're going to want. The feature that we use on the calculator in order to find the proportion from the z-score, we're going to go back to second vars, but this time we're going to choose number 3 for inverse norm. All right, let's talk about normal distribution calculations. To begin with, we need to know what the shape of the distribution is, and we need to know what the mean and standard deviation are. With that information, we're going to sketch and shade the probability distribution and the area of interest. Next, we're going to do the calculations, of course, showing the work. If we're using table A, we're going to put down all the pertinent values. Even if we use the calculator feature, we're going to show the calculation of the z-score in our work. Last of all, we're going to go back to the question and make sure that we answer the question that is being asked. Let's take a look at an example about Tiger Woods. On the driving range, Tiger Woods practices his swing with a particular club by hitting many, many balls. Suppose that when Tiger hits his driver, the distance the ball travels follows a normal distribution with mean 304 yards and a standard deviation of 8 yards. What percent of Tiger's drives travel at least 290 yards? So the very first thing we're going to do is write down the information that's been given to us and sketch and shade our area of interest. We've done step 1 and we have our area of interest sketch and shaded. The next thing that we're going to do is calculate the z-score. Now that we have the z-score, we're going to go to table A and find the area associated with that score, or we're going to use the normal CDF function on our calculator. Table A and normal CDF give us the same value, and the percent of Tiger's drives that travel at least 290 yards is about 96%. Now let's talk about what percent of Tiger Woods' drives go exactly 290 yards. If you have been a student of calculus, then you know that you cannot find the area under a single value or above a single value. And what that translates into is we're never going to be able to determine with a normal distribution, which is a continuous distribution, the percent or the proportion of exactly a single number. Think of it as when we have area under a curve, what is the area of a single line? And we know a single line has no area. So the answer is we cannot find that. Next, we want to find what percent of Tiger's drives are between 305 and 325 yards long. So once again, we're going to start with a sketch and shade. Here's our normal curve and our shaded area of interest. And I'm going to caution you, while I am copying and pasting images, you definitely want to get in the habit of drawing the curve yourself and shading, because when it comes to the exam, that's exactly what you're going to need to do, both on your test, chapter test, and on the exam. So get practice, even though it's a little bit painful at the beginning to kind of get used to sketching and shading. Remember, it doesn't need to be perfect. It just needs to be labeled well enough for you and me to read. All right, let's find the z-scores associated with the two values of interest, 305 and 325. When using Table A, the z-scores are only listed to the hundredths place, so there's no point in going 3 decimal places on the z-score. And so we know we're going to be a little bit less accurate than when we use the normal CDF feature in our calculator. The format for the normal CDF is lower boundary, then upper boundary, then mean, and standard deviation. So we can either put the z-scores in there with a mean of 0 and a standard deviation of 1, or we can put the original values in with the original mean and standard deviation. All in all, the percent of Tiger's drives that travel between 305 and 325 yards is about 45%. Now, if we need to work backwards, we can remember we're going to be using that inverse norm feature in the calculator, or we're going to start at the inside of Table A and work our way out towards the z-score. In trying to find the IQR for Tiger's drives, we're going to start by finding the 75th percentile and the 25th percentile. You can see two different methods here. One of them is using Table A in red, and the other one is using the calculator feature inverse norm in blue. We basically get the same answer though, so that's comforting. Okay, let's move on. Assessing normality means we want to determine whether a particular set of data follows a normal distribution or approximately follows a normal distribution. Here we have some data. Unemployment rates for the 50 states range from lowest to highest. In a minute, you're going to pause the video, put this data into your calculator, calculate the one variable statistics, and then draw the histogram, and then turn the video back on. Okay, we've got the mean and the standard deviation. We've also graphed the histogram. And what we see is that the histogram is approximately symmetric, but it's really not clear whether we can assume that it's normal or not. So we're going to have to test the data against the empirical rule. We're going to start with some calculations. The mean plus or minus the standard deviation 1, 2, or 3 times. That's going to establish the boundaries for us to check the data against. When we start out at the mean and go to the left 1 standard deviation and to the right 1 standard deviation, we end up with these boundaries of 6.457 and 10.907. That should represent 68% of the data. Let's see if it does. I've highlighted all the data values between those two boundaries. When we count them, we find that there are 36 out of 50, or 72%. So this is close to 68%. In fact, it's even more data close to the mean. Let's try with 2 standard deviations away from the mean. Start by calculating the boundaries. We've got the boundaries now of 4.232 to 13.132, and that needs to represent 95% of the data for it to follow the empirical rule. So let's highlight the additional data values that would be included. And it looks like all but 2 of them will be. So that means we've got 48 out of 50, which is 96%. For the sake of completeness, let's go ahead and calculate the boundaries for plus and minus 3 standard deviations from the mean. We've got those boundaries, and that will encompass the last two values because our boundaries are 2.007 and 15.357. That's supposed to represent 99.7% of our data, but it does in fact encompass all 50 data points. So we're at 100%. And at this point, we are satisfied that this data follows a normal distribution or very close to it. Now, there's one more thing that we can do, and that is to plot the normal probability plot. I'd like for you to go back to your calculator, and you're going to go back to the stat plot. In order to graph the normal probability plot on the TI-83 or 84, we first have to put the data in, which we already have it in there because that's how we made the histogram. We're going to go to stat plot, which you remember is second y equals. Under second y equals, you're going to select the last plot on the right-hand side. Next, indicate the appropriate list. Remember, we do that with second and then whatever the number is. And the data axis is going to say X. What that means is your horizontal axis is going to have the same scale as your histogram had. At this point, you're ready to zoom 9. Remember that when you graph the normal probability plot on your paper, your axis needs to be the same axis that you use for your histogram, so label and scale, but your vertical axis is actually graphing the z-score for each and every one of the data points. Now, what are we looking for on the normal probability plot? The question is it linear? If the normal probability plot is approximately linear, which it is in this case, then the data that we were working with to begin with is approximately normally distributed. So it's not always going to show up this way. You can try it with a right skewed distribution. In this case, I want you to notice that we have some separation way over on the left and way over on the right. Those are representing the two tails of the data. And then you see a lot of data packed in this middle area. And that is showing the high frequency towards the center. So that concludes our 2.2, and I know it was jam-packed full of information. If you have questions, bring them to class. As always, this means you're ready for practice problems.